Hello there. In this video, I am going to be concentrating on identifying types of polar curves. This is not going to be a video on an in-depth analysis of graphing polar curves, rather just identifying polar curves, and we will be using Desmos to assist us in this. So let's get started. First of all, the types of polar curves that we're going to be looking at here can fit the general form of r equals c plus a sine of b theta, or e equals c plus a cosine of b theta. Let's take a look first at circles. So circles are going to have the form r is equal to a sine of theta, or r is equal to a cosine of theta. In other words, there's no c value and there's no b value. So c is essentially 0 and b will essentially be 1. So some examples of this would be r is equal to 3 sine of theta, or r is equal to negative 5 cosine of theta. So let's take a look at Desmos. So here I have my general formula, r equals c plus a sine of b theta, r is equal to c plus a cosine b theta. Let's take a look at the sine function first. Now I have my sliders set so that c is 0, b is 1, and right now a is 1. So this graph right here, this curve, is simply the curve of r is equal to the sine of theta. Well, let's see what happens as we let a get bigger. As a gets larger and larger by moving the slider, you can see that the radius of the circle is getting larger and larger and larger. As we go into negative a values, the radius gets smaller and smaller, and when it becomes negative, it reflects over the x-axis and then becomes larger and larger and larger, but below the x-axis. All right, so setting a back to 1, and then let's take a look at the cosine graph. Well, the same thing is going to happen with cosine. As a gets larger, the radius gets larger. When a becomes negative, it reflects over the y-axis and then becomes larger on the left side. And if we wanted to, we could play around with these with both of them and see how sine and cosine are both affected at the same time by changing the a value. All right, those are circles. Next up, we want to take a look at what are called rose curves. So rose curves are of the form r is equal to the sine of b theta, r is equal to the cosine of b theta. In this case, once again, the c values are 0 and the a values, they can exist. We can have an a value, and we'll see what happens when we change those, but that's not important for this discussion because what determines a rose curve is the value of b. So an example would be r is equal to the sine of 3 theta, or r is equal to the cosine of 8 theta. Let's take a look in Desmos at what happens when we change the b values. So a I'm going to keep at 1, c I'm going to keep at 0, and let's just change b now. Let's just look at the sine function. I'm going to, instead of using the slider at first, I'm just going to manually change this and let b be equal to 2. Aha! Well, that doesn't look anything like a circle. This is what is referred to as a rose curve. And it gets its name from the fact that it looks somewhat like a flower with petals on it. And each one of these loops is referred to as a petal. Now, one thing that's important to realize is that there's a relationship between the number of petals and the b value. When the b value is even, such as 2, the number of petals will be twice the b value, which is 4. If I change the b value to 6, we're going to have 12 petals. if I change the B value to 12, you can count them, but take my word for it, there are 24 petals here on this rose curve. If the B value is odd, like 3, or like 5, then the number of petals is equal to the B value. So an odd B value, the number of petals equals the B value. An even B value, the number of petals will be 2 times the B value. Now, if we did switch the A value, notice that what that does is it just makes the petals larger and smaller. And if we make A be negative, it reflects over the x-axis. Remember, this is the sine function. Same thing will hold true with the cosine function. So now we're looking at the cosine function, and we have 5 petals. Let me put in just 4 petals, or 8 petals, B of 4. And changing the A value makes the petals larger or smaller. And when it becomes negative, it reflects it over the y-axis. So that is a rose curve. You can identify a rose curve because you have some multiple angle here. 3 times the angle, 8 times the angle. That's the B value. The next type of curve we're going to look at is called a cardioid. And this is when we introduce the C value. So we're going to have R is equal to C plus A sine theta, and R is equal to C plus A cosine theta. In order to be a cardioid, C must be equal to A. So as an example, we could have R is equal to 8 plus 8 sine theta, or R is equal to negative 3 minus 3 cosine of theta. We can have a B value, but again, the B value is not important for this discussion. The only thing that's important for this discussion are the A and the C values. So let's take a look at Desmos. In Desmos now, let's let B simply be equal to 1 to simplify the discussion. And let's start off with an A value of 1. And let's go back to the sine function. And now I'm going to introduce the C value, which will also be 1. And so we get something that looks like this. That is a cardioid. The A value and the C value are both equal to 1. If I let C be equal to 2, and I let A be equal to 2, I have the same basic shape. This is called a cardioid because with a little bit of an imagination, it looks somewhat like a heart. A cardioid from the cosine function is simply going to be kind of sideways from the sine function. And we can let A be negative, and then I have to let my C be negative, and we get a cardioid. It looks like that. Okay, the next function that we're going to look at is similar to a cardioid. These are called limicons. So I think this is what, number 4. So a limicon has the same form. R is equal to C plus A sine of theta. R is equal to C plus A cosine of theta. The only difference here, C is not equal to A. If C is going to be less than, or let's say, yeah, so C is less than A. If C is less than A, we have a dimpled limicon. And I'll show you what that is in just a second. If C is greater than A, then we have an inner loop. So some examples would be R is equal to 8 plus 3 sine of theta, and R is equal to 2 plus 5 cosine theta. Now, the function with sine, because the c value is greater than the a value, this would have an inner loop. Over here with the cosine function, because the c value is less than the a value, we will have a dimpled limicon. So let's take a look at those in Desmos. Let's look at the sine function first. Again, I'm going to let b be equal to 1, and let's let a be equal to 2 and c be equal to 1. All right, so c is less than the a value, and so we have an inner loop. If we let the c value be larger, then we have what is, let's say, well, let's not make it that much larger. Let's just go to 3, and let's let a be equal to 1. 2. So a is equal to 1, c is equal to 2. We don't have an inner loop. It is somewhat what we call dimpled. There we go. There's more of a dimpled. Now, if a is equal to c, then we end up with a cardioid. So what happens if we end up, let's c be equal to 4 and let a be equal to 7. We have an inner loop. So the a value is larger than the c value. We have the inner loop. And same thing will be true with the cosine function. And so we can change, notice if we change the a values. So if we keep the c value of 4 and my a value becomes a 4, we're going to have a cardioid. As a becomes smaller and smaller, we have the dimple. We have the dimpled limicon. It gets so dimpled it almost looks like a circle for a little while until it dimples in the other direction as a becomes negative, and then it turns into an inner loop. So the inner loop, the dimpled limicon, and the cardioid are all related through the a value and the c value. It's the relative sizes of each. Okay, those are the basic types of polar curves that we're going to be looking at in this particular video. There are other polar curves. Very quickly, we have a polar curve. R is equal to some constant a. And if we have R is equal to some constant a, that is simply going to be a circle centered at 0, 0 with a radius of a. So that radius is going to be equal to a. So as an example, R is equal to 3 is simply a circle centered at the origin with a radius of 3. All right, and so then we also have theta equals some constant b. Well, that is simply going to be a line. And the line is going to be a straight line. And that's because the theta, the angle here, theta, is constant. If theta is some constant b, then the angle never changes. And if the angle never changes, the slope never changes. And the slope, which we know is the change in y over x, the slope is change in y over x. Well, if this is the change in y and this is the change in x, well, that's also the opposite side of a right triangle over the adjacent side, which is defined as the tangent of theta. So the slope is the tangent of theta. So these are two very simple equations. Theta equals some constant and r equals some constant. And those are all of the different types of polar curves that you will need to be able to recognize in this class. Once again, this is not a video on a detailed analysis of graphing them, but rather to be able to look at the equation of a polar curve and say, that is a cardioid, that is a limicon with an inner loop, that is a straight line, or that is a circle, and be able to visualize in your mind what type of curve it is. All right, that's it. Hope you enjoyed the video.